Hello. The periodic table is an incredibly useful tool. The periodic table has a unique structure that holds a lot of information within it. The value of this structure is that it can be used to determine much information about every single element that is within the table. The point of this lesson is to learn to understand this structure and use it to be able to draw an atomic model for each of the elements in the table. At the end of the lesson, we will look at the element iron with chemical symbol Fe, and we will draw the atomic model for iron based solely on its position here in the periodic table. So let's get into it. If you've ever heard someone talking about atoms or atomic structure, you've probably seen an image like this at some point. And you know that this thing in the center is referred to as the nucleus. Okay, and then the nucleus is composed of protons and neutrons, and these things floating around the outside are referred to as electrons, and the thing that the electrons float around the nucleus in is called the electron orbital. Let's take a closer look at the atomic structure. Here we have a single proton at the nucleus, and it has a positive sign showing that it has a positive electrostatic charge. The electron, however, has a negative electrostatic charge. That's why the electron is attracted to the nucleus and orbits the nucleus, is because opposites attract when we were talking about electrostatic charges. So neutrons do not have a charge. The main purpose that they serve is to stabilize the nucleus. So if we add another proton, we must add another electron, otherwise this atom will take on a charge. And sometimes atoms take on a charge during chemical reactions, but usually they are most stable when they do not have a charge and the electrons and protons are balanced. Here we have 2 positive protons and 2 negative electrons, and so this atom is balanced. Remember, the neutrons do not have a charge, so they do not affect the charge of the atom. They only serve to stabilize the nucleus. Now, if we add a third electron, we must also add another electron orbital. This is because electron orbitals can only hold 2 electrons, or what we call an electron pair. Also notice that when I added this third electron, I also had to add a third proton to the nucleus to keep this atom balanced. So don't forget, electron orbitals can only hold 2 electrons, or what we call an electron pair. So if we take a look at the periodic table, you can see there's a lot of elements, and all these elements are different. They do different things in the world we live in. You're probably familiar with oxygen that you breathe, or gold that we use in a lot of jewelry and electronics, and you're probably also familiar with calcium. That's an important mineral in our bones. So what is it that makes all of these elements different and able to do their specific jobs? Well, the answer is their atomic structure. And if we go back to looking at our atomic structure, we see the atomic structure is not very complicated. It's simply the nucleus, which is composed of protons and neutrons, and the electrons, which orbit around the nucleus in their electron orbitals. So the different elements must have different combinations of these few characteristics. So if we take a look at the structure of the periodic table, we can see that it's organized. And the structure is organized with 3 features, which are first the columns, the second is the rows, and the third is it's segmented. Okay, you have this vertical rectangular segment on the left. In the middle you have the horizontal rectangular segment with another horizontal rectangular segment below it, and on the right we have basically this square segment. So once again, the periodic table is organized with 3 features: the columns, the rows, and the segmented blocks. And where an element sits on the periodic table determines the atomic structure of that element. And we're going to look into this table and see how we can break down the atomic structure of an element just by where it sits on this table. One important thing that I want to point out about the periodic table is that if you look at this little spot right here, you see it has these numbers 57 through 71, and that's corresponding to these elements right here, 57 through 71, and below that you have 89 through 103, which corresponds to these elements 89 through 103. That means that this block is really supposed to be inserted right here, and that would make the periodic table look like this. But you pretty much always see the periodic table in this format right here, and that's because it's not as long and it's a lot easier to put into documents like 8.5 by 11 or on a computer screen. So the point of this lesson is to determine an element's atomic structure based on its position in the periodic table. And in order to do that, you need to be familiar with the structure of the periodic table, which I said earlier has three features: the rows, the columns, and these segmented blocks. So first we're going to be taking a look at the rows. Now the rows represent what you call principal levels, which are like layers of an onion, and atoms have layers of an onion, and we call these layers principal levels. And the principal levels are what hold the electron orbitals. So each principal level can hold several electron orbitals, and elements in the first row have one principal level. Elements in the second row have two principal levels, and elements in the third row have three principal levels. Now, if you noticed right here that these yellow ones are actually in the fourth row, but they're categorized yellow to show that they're actually still in the third principal level. And you're probably thinking that doesn't make any sense, and it does make sense, but I'm gonna have to get to that later. So let's just keep going with this and we'll come back. Okay, this shows the fourth principal level. This shows the fifth principal level, sixth principal level, and seventh principal level. Now, remember the color categorization. So this row is actually, because it's this light green, it belongs to the fourth principal level, and this dark green belongs to the fifth principal level. Okay, so once again, we're talking about how the structure of the periodic table is reflective of the atomic structure for each of the elements within the periodic table. We just talked about how the rows represent what we call the principal levels, which hold the electron orbitals, and we can think of the atomic structure like an onion having layers, and each row represents a new layer to the atomic structure. Now, as we go down the periodic table, you see we're gaining layers, and so now we're going to talk about the columns of the periodic table, and how as we go across the columns we gain electrons, and we continue to build our atomic structure. So first, in the first column at the top row, we have hydrogen. Okay, now hydrogen, let's turn this off and on again. As you see that hydrogen has one principal level or layer, and it has one because it's in the first row, and it has one electron because it's in the first column. Okay, so that tells us a lot about the atomic structure of hydrogen, that it has one principal level and one electron. Now, as we go to the second column, in the first row there's two columns, okay, because there's just two of these little elements, and then the next one to the right is helium. Now notice as I activate helium, I got a second electron because once again the columns are reflective of electrons. Okay, so now when we go to the second row, we have lithium, and we start a new row, so we're in a new principal level now, and we have a new electron. Notice that one more time. Okay, now to the right in the second column of lithium, we have beryllium, and we have two electrons, because remember, column is reflective of electrons. And then after beryllium, we have boron with 3 electrons in the third row, carbon with 4 electrons because it's in the fourth column. Then we have nitrogen in the fifth column with 1, 2, 3, 4, 5. Check that out again. We just gained a fifth one. Then we have oxygen, okay, in the sixth column with 1, 2, 3, 4, 5, 6 electrons. And then fluorine with 7, and then finally neon with 8. Now, one thing to take note of is neon is in the final column. the eighth one of this row. 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 electrons. Now I want to bring up some terminology right now. For neon, it only has two layers because it's in the second row, or 2 principal levels. So the electrons in the outermost principal level or shell or layer, whatever you want to call it, those outermost electrons are called the valence electrons, and they are what are involved in chemical reactions because they're on the outside of the atomic structure. They are on the outside, they see other elements, they react with other elements, they're involved in chemical reactions. Once again, the valence electrons are on the outside and involved in chemical reactions. When the principal level is complete, it has all of the electrons filled, that element is happy. Okay, we call it, when we have a completed valence shell, we call that an octet, and that makes the element happy. They like having an octet, and so neon is very unreactive. Same with helium. Even though it only has 2 electrons, it's still complete because that's all the electrons that are in the first row, and so helium is also non-reactive. All these elements in the far right column we call the noble gases because they are unreactive. Okay, so if we keep going into our third row, we start we're in a third row now, so we start a new principal level, and we're in the first column, so 1 electron. Hopefully you guys are starting to see the pattern here. Then we have magnesium, second row, 2 electrons. Aluminum, third column, 3 electrons. And then silicon with 4, phosphorus with 5, sulfur with 6. Now, one thing I want to point out right now is that you see the elements in the same column have the same number of valence electrons. Okay, so that means that these elements are going to have similar properties because they have the same number of valence electrons available to react. That's an important point to remember, is the elements in the same column have similar chemical properties, and we call the columns groups. So elements in the same group have similar characteristics. Just like we saw that the noble gases at the far right are in the same column, are all unreactive. That's a similar chemical property. Okay, so after sulfur we have chlorine with 7 similar properties to fluorine above it, and then argon, which is another noble gas with a complete octet. Okay, when we get into the fourth row, we're going to see something new here. Okay, potassium, new row, new layer, first column, 1 electron. Calcium, second column, 2 electrons. Now, when we get into this weird one, this offset row right here with scandium, okay, notice that scandium, that did not go into the outermost valence shell. That electron did not go in the outermost valence shell because this row is yellow. Even though it's in the fourth row, it's yellow, so that means it belongs to the third principal level, and that's why this electron went into that yellow layer. Okay, which is the third principal level. So these elements, and when you add electrons to these elements in this segment right here, this block of the periodic table, which is called the D block, we're going to find out later, these are not valence electrons because they are not on the outside. They're being added to the previous row. Okay, so those are not valence electrons. After scandium, you got titanium. Okay, you just added another one to this third principal level, and we just keep going. Vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, now all of the yellow elements are full. Okay, so that means that this third principal level, all the yellow rows are full of electrons. Okay, this means this third row can hold 18. Okay, because we got 10 electrons right here in this middle block, the D block, and so we are completely loaded at this point. Hopefully you guys are starting to see the pattern of how the periodic table is reflective of the atomic structure. Remember, the periodic table has three features. It has the rows, the columns, and these segmented blocks. Okay, we've just talked about the rows and the columns, about how the rows are representative of the layers to the atomic structure, and the columns are representative to the electrons that go into these layers of the periodic table. Next, we're going to talk about these segmented blocks. One thing I want to remind you guys is that the principal levels are not electron orbitals. The electron orbitals that hold the electrons are within the principal levels. So each of these layers that's a principal level is going to have several orbitals, because orbitals can only hold 2 electrons or an electron pair. So it's easy to know how many orbitals are in each principal level, because you just take the number of elements in that principal level. So for example, in the third principal level, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons, or 18 elements. And so that if you're going to find out how many orbitals there are, you're going to take the 18 and divide it by 2, because each orbital holds 2 or a pair. And so that means that there are going to be 18 divided by 2 is 9. So there's going to be 9 orbitals total. Okay, 9 orbitals total. Another thing I want to point out right now is the periodic table. Basically, as you go left to right, top to bottom, the atoms are getting bigger. They're getting more layers with each row and getting more electrons with each column. So that's a very important point. Basically, what sets the elements apart is their size. Okay, and remember that size gets bigger as you go left to right, top to bottom of the periodic table. Now we're going to take a look at the final feature of the periodic table, which is the segmented blocks. And if you look, there is 4 segments. There's the S block, the D block, the P block, and the F block. And there's one exception over here where this red one's kind of on its own, and you're like wondering, why doesn't it fit over here with the other S block? And the answer is because this element is helium, and in the first row we only have 2 columns, okay, which, remember, the columns are representative of the electrons. And so helium has all of its electrons, even though it only has 2 in this row. So remember, when elements have completed their valence electron shell, they're unreactive. We call those noble gases. And that's why helium is over here on the right, to group it in with the other noble gases. Even though it doesn't have an octet, it has 2 electrons, it's still complete and it still has the same properties, and it's grouped in over here with the other noble gases. So you're probably wondering by now, what the heck is a block? And the blocks are representative of different types of electron orbitals. So each row, remember, represents principal levels which hold electron orbitals, and the columns represent electrons. So the principal levels are composed of different blocks. The first principal level just has S block. The second principal level has S and P block. And then when we get down to the fourth level, we have S, D, and P block. And those blocks are split up to represent different type of electron orbitals, which we call the S orbitals, the D orbitals, the P orbitals, and the F orbitals. And we categorize those different types of orbitals because they are unique. They have different shapes in which the electrons travel in. They have different energies, and these different type of orbitals contribute to the characteristics of the elements. So an element right here in the third row and fifth column, which is nitrogen, that element is going to have 2 different types of orbitals. It's going to have S orbitals and P orbitals, and this is good information to know. So the big takeaway is that each row or principal level is split into segmented blocks, and those are representative of the orbitals. So remember, look again at this fourth row. This whole row is split into a red and a blue and a p segmented block, which is representative of the s orbitals, the d orbitals, and the p orbitals. So in that whole principal level, we have 3 different types of orbitals that all behave differently. So going back to this issue we talked about earlier of the principal levels being offset, here you have the third principal level having the D block being offset down 1. I didn't really talk about why that is earlier, I just skimmed over it, but now that we know about the S, the P, and the D orbitals, we can answer that question. And remember when I said as you go left to right, top to bottom, the atomic structure gets bigger because you're gaining layers and you're gaining electrons? Well, this periodic table is ordered left to right, top to bottom, but it's ordered in terms of energy, not exactly distance from the nucleus. So this third principal level, which is split into the S, the P, and the D orbitals, this is offset like this because the S orbitals are the lowest in energy of the third principal level, then the P orbitals come next, and then the D block is down 1 because the 4 S orbitals are actually lower in energy than the 3 D orbitals. Okay, so that's why that's like that. That's because the 3D orbital is not up here, because that would mean that the 3D orbital is lower in energy than the 3P, because remember, this is ordered in terms of energy from left to right, top to bottom. So this shows you that the order in energy is the 3S, then the 3P, then the 4S, and then the 3D is actually the highest in energy. So let's now take what we learned to analyze the atomic structure of a particular element on the periodic table. So iron with chemical symbol Fe down here in the 4th row. You know it's in the 4th row, so it has 4 layers around the nucleus, 1, 2, 3, 4. And you know that its valence electrons are in the 4th principal level, and you know it has 2 electrons in its valence shell because in the 4th principal level, which is this light green, you just have 2 columns, 1, 2, okay, and all of its other electrons are in the other principal levels. So let's just go down to the 3rd principal level. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. So that's why we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In the 2nd principal level, you have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And in the 1st principal level, you just have 2. Okay, so in one final thing is you can tell that the 1st principal level, it just has the S orbitals. In the 2nd principal level, it has the S orbitals and the P orbitals. 3rd principal level, it has S, P, and D orbitals, and in the 4th and outermost valence shell, it only has S orbitals. So we've just drew the complete, a nice little model of the complete atomic structure of iron, solely based on looking at where it is on the periodic table, which is incredibly useful information. And later in other lessons, we'll see how this is useful, to see how it reacts with other elements, to see what kind of molecules it might form, etc. Hopefully you learned a lot from this lesson, and obviously this is a lot of information, but I urge you to re-watch it and slow down in sections that you have a hard time until you understand this, because this is basically the building blocks of understanding all future chemistry courses. Thanks for watching.